Welcome to this soothing exploration of the physics of tidal forces. As we embark on this gentle journey, we will delve into the rhythmic dance between celestial bodies, where the moon and the sun exert their gravitational pull on the Earth's oceans. This gravitational interaction creates the tides, a phenomenon that has fascinated humans for centuries. Through calming narratives and serene descriptions, we will explore the fundamental principles of tidal forces, their effects on our planet, and the intricate balance that governs these natural rhythms. Let your mind drift as we uncover the beauty of the universe's gravitational embrace, guiding you into a state of relaxation and tranquility. Tidal forces are a result of gravitational interactions, primarily between the Earth, the Moon, and the Sun. Understanding these forces begins with the fundamental concept of gravity itself, an invisible force that draws objects toward one another. Sir Isaac Newton first formulated the universal law of gravitation in the late 17th century, which states that every mass attracts every other mass with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This means that larger masses, like the Moon and the Sun, have a more significant gravitational pull than smaller bodies, like the Earth's oceans. The effect of this gravitational pull is most observable in the way it influences the movement of water in oceans and seas, creating the rhythmic rise and fall known as tides. The Moon plays a crucial role in the creation of tides. As it orbits the Earth, its gravitational pull affects the water in the oceans, causing it to bulge out in the direction of the Moon. This bulge represents high tide. On the side of the Earth opposite the Moon, there is also a bulge, though it is not directly caused by the Moon's gravity. Instead, this bulge is a result of the centrifugal force created by the Earth-Moon system's rotation. As the Earth rotates, the water on the far side is left behind, creating another high tide. In between these two bulges, the water level recedes, resulting in low tides. This intricate balance between gravitational pull and centrifugal force leads to a predictable pattern of high and low tides that occurs approximately every 6 hours. The Sun, despite being much farther away than the Moon, also has a significant influence on tidal forces due to its massive size. The gravitational pull of the Sun is about half as strong as that of the Moon, but it still plays a vital role in the overall tidal pattern. When the Sun, Moon, and Earth align, which occurs during full moons and new moons, we experience spring tides, where the tidal range is at its maximum. Conversely, during the first and third quarters of the lunar cycle, when the Sun and Moon are at right angles relative to the Earth, we experience Neap tides, where the tidal range is at its minimum. This interplay between the gravitational forces of the Sun and the Moon creates a dynamic that shapes the tidal experience across the globe. To fully appreciate the complexities of tidal forces, we must delve deeper into the concept of gravitational pull. Gravitational pull is not uniform across the Earth's surface. The strength of gravity varies depending on factors such as altitude, latitude, and the Earth's shape. For example, the gravitational force is slightly weaker at the equator than at the poles due to the Earth's rotation and its equatorial bulge. This variation can influence local tidal patterns, as areas with stronger gravity may experience slightly different tidal behaviors compared to those with weaker gravity. Historically, humans have observed tides for thousands of years, recognizing their significance for navigation, fishing, and understanding the natural world. Ancient civilizations, including the Greeks and Romans, noted the correlation between the moon's phases and the tides. The term tide itself is derived from the Old English word tid, which means time, reflecting the cyclical nature of this phenomenon. Early mariners learned to use the tides to their advantage, timing their voyages to coincide with high tides for easier navigation through shallow waters and coastal areas. The relationship between the moon's phases and the tides became a crucial aspect of maritime culture, influencing everything from fishing practices to the timing of festivals and rituals. As we explore the basic principles of tidal forces, it is essential to recognize the rhythmic nature of tides and how they connect us to the broader universe. The regularity of tides provides a comforting reminder of the predictable patterns that govern our world. When we observe the tides, we are witnessing the gravitational ballet of celestial bodies that has been happening for billions of years. This cosmic dance not only shapes our oceans, but also influences the life that thrives within them. In the context of modern science, tidal forces are studied through various scientific disciplines, including physics, astronomy, and oceanography. Researchers utilize mathematical models to predict tidal patterns, accounting for the gravitational influences of the moon and sun, as well as local geographical features such as coastlines and underwater topography. These models allow scientists to forecast tidal heights and timings, which are crucial for various industries, including shipping, fishing, and coastal management. Tidal forces also have implications beyond the immediate impact on ocean levels. They are a vital aspect of Earth's climate system, influencing ocean circulation patterns and consequently weather systems. The movement of tides helps to mix ocean waters, distributing heat and nutrients throughout the oceans. This mixing is essential for maintaining healthy marine ecosystems, supporting biodiversity, and sustaining fisheries that many coastal communities rely on. As we drift deeper into the science of tidal forces, we begin to appreciate the interconnectedness of various natural systems. Tides are not just a local phenomenon, they are a reflection of the gravitational relationships that exist on a planetary scale. The moon's orbit around the Earth is not a simple path. It is influenced by the gravitational pull of the Earth, the Sun, and even other celestial bodies. This complex interplay creates variations in tidal patterns, leading to diverse coastal experiences around the globe. In addition to the scientific understanding of tidal forces, there is a cultural and spiritual dimension to tides that has captivated humanity throughout history. Many cultures have developed myths and legends surrounding the moon and its influence on the tides. The moon is often seen as a symbol of change and transformation, reflecting the cyclical nature of life itself. Coastal communities have long celebrated the tides, incorporating them into their cultural practices and traditions. Festivals, rituals, and storytelling often revolve around the ebb and flow of the tides, emphasizing the deep connection between people and the natural world. As we continue to explore the physics of tidal forces, we will delve into the specific role of the moon in greater detail. The moon's gravitational effects on Earth are profound and far-reaching. Its influence extends beyond the mere creation of high and low tides. It shapes the very fabric of life in our oceans and on our shores. By understanding the moon's role, we can gain deeper insights into the rhythms that govern our planet and our lives. We will examine how the moon creates high and low tides, exploring the concept of the tidal bulge in more detail. We will also look at the lunar phases and their influence on tidal patterns, revealing the intricate connections between celestial movements and the natural world. Furthermore, we will discuss the moon's orbit and its effect on tidal patterns, highlighting the dynamic nature of this relationship. Myths and cultural significance surrounding the moon's influence will also be explored, enriching our understanding of how humanity has perceived and related to this celestial body throughout history. As we prepare to embark on this next phase of our exploration, let the soothing presence of the tides wash over you. Allow yourself to relax and embrace the calmness that comes with understanding the natural rhythms of our universe. The physics of tidal forces is not just a scientific inquiry. It is an invitation to connect with the world around us, to appreciate the delicate balance that sustains life on our planet. As we move forward, May you find peace and tranquility in the knowledge that we are part of a much larger cosmic dance, one that continues to unfold with every rise and fall of the tide. Let your mind drift gently as we uncover the mysteries of the moon and its profound influence on the tides. As we continue our exploration of tidal forces, we turn our attention to the role of the moon. The moon, our constant companion in the night sky, has a profound influence on the Earth's tides. This influence is not merely a poetic notion, but a scientific reality, deeply rooted in the physics of gravitational interactions. The gravitational pull of the moon on the Earth is the primary driver of the tidal phenomenon, creating a rhythmic dance of water that ebbs and flows across our oceans. Understanding how the moon creates high and low tides requires a closer look at the mechanics of gravitational forces. When we consider the Earth and the moon, we must remember that both bodies exert gravitational forces on one another. The moon, despite its distance from Earth, has a significant gravitational pull that affects the water in the oceans. As the moon orbits the Earth, it creates a tidal bulge on the side of the Earth that faces it. This bulge is the result of the water being drawn toward the moon's gravitational field. Conversely, on the side of the Earth opposite the moon, another bulge occurs. This phenomenon happens because the Earth itself is being pulled slightly toward the moon, while the water on the far side remains less affected by this pull. The result of this gravitational interaction is a pair of high tides and low tides experienced on Earth. As the Earth rotates on its axis, different locations pass through these tidal bulges, leading to the rhythmic rise and fall of sea levels. Typically, most coastal areas experience 2 high tides and 2 low tides within a 24-hour period, a pattern known as semi-diurnal tides. Some locations, however, may experience only 1 high tide and 1 low tide each day, known as diurnal tides. This variation is influenced by the specific geography of the coastline and the depth of the ocean. The moon's phases also play a crucial role in determining the intensity of the tides. During a full moon and a new moon, the sun, moon, and Earth align. This alignment causes the sun's gravitational pull to work in conjunction with the moon's pull, resulting in higher high tides and lower low tides, known as spring tides. Conversely, during the first and third quarters of the moon, the sun and moon are at right angles relative to Earth. This positioning leads to a reduction in tidal ranges, producing lower high tides and higher low tides, known as neap tides. The moon's orbit is not a perfect circle, but rather an elliptical path. This means that the distance between the Earth and the moon varies over time, affecting the strength of the gravitational pull. When the moon is closest to the Earth, a position known as perigee, the tidal bulges are more pronounced, leading to higher tides. Conversely, when the moon is at its farthest point, or apogee, the tides are less pronounced. This variation adds complexity to the tidal patterns experienced on Earth, creating a dynamic interplay of forces that govern our oceans. Culturally, the moon has held immense significance throughout history. Many ancient civilizations observed the moon's phases and their effects on tides, often weaving these observations into their myths and folklore. For seafaring communities, the moon's influence on tides was crucial for navigation and fishing. The waxing and waning of the moon not only guided their journeys, but also dictated the best times to harvest from the sea. The connection between the moon and tides is so deeply ingrained in human culture that it has inspired countless stories, poems, and art throughout the ages. As we delve deeper into the gravitational effects of the moon, we also uncover the importance of tidal bulges. These bulges are not static. They shift and change as the Earth rotates and as the moon orbits. The tidal bulge moves in response to the gravitational pull of the moon, creating a dynamic system that is influenced by various factors, including the Earth's rotation, the moon's orbit, and even the sun's gravitational pull. This intricate relationship results in a complex pattern of tidal flows that varies across different geographical locations. Understanding the concept of tidal bulges also requires us to consider the role of the Earth's rotation. The Earth spins on its axis approximately every 24 hours, which means that different regions of the planet experience the tidal bulges at different times. This rotation is responsible for the timing of high and low tides. As the Earth rotates, a point on the surface will pass through the tidal bulge created by the Moon's gravitational pull, leading to a high tide. As that point rotates away from the bulge, it will experience a low tide. The interplay between the Moon's gravitational pull and the Earth's rotation creates a fascinating dance of water. The oceans respond to these forces with a predictable rhythm, allowing scientists to forecast tidal patterns with remarkable accuracy. This predictability is essential for various human activities, including navigation, fishing, and coastal management. In addition to the gravitational forces at play, we must also consider the effects of local geography on tidal patterns. Coastal features such as bays, estuaries, and the shape of the shoreline can significantly influence the height and timing of tides. In some areas, the tidal range can be amplified due to the funneling effect of narrow bays, leading to higher tides. Conversely, in other regions, the same gravitational forces may result in minimal tidal changes due to the unique configuration of the land and sea. As we reflect on the historical context of tidal observations, we recognize the contributions of early astronomers and scientists who sought to understand these natural phenomena. The meticulous observations of tides, recorded by ancient mariners, laid the foundation for our modern understanding of tidal forces. Figures such as Galileo and Newton made significant strides in explaining the mechanics behind tides, linking them to gravitational forces and celestial movements. Their groundbreaking work paved the way for future generations of scientists to explore the complexities of tidal interactions further. The Moon's influence on tides extends beyond mere scientific observation. It has also shaped our understanding of time. Many cultures have used lunar cycles to establish calendars, marking the passage of time in relation to the Moon's phases. This connection between the Moon and timekeeping reflects the deep-rooted relationship between natural phenomena and human existence. As we immerse ourselves in the intricacies of tidal forces, we begin to appreciate the elegance of the gravitational interactions that govern our oceans. The Moon's gravitational pull, combined with the Earth's rotation and the influence of local geography, creates a symphony of rhythms that resonate across the planet. This dynamic interplay is a reminder of the interconnectedness of natural forces, inviting us to consider our place within this vast and beautiful universe. In summary, the role of the Moon in creating high and low tides is a complex interplay of gravitational forces, Earth's rotation, and geographical features. The tidal bulges formed by these forces lead to predictable patterns of ebb and flow in our oceans. Through the ages, the Moon has captivated human imagination, influencing culture, navigation, and our understanding of time. As we continue our exploration of tidal forces, we will delve into the Sun's contribution to this intricate system. The Sun, while not as close to Earth as the Moon, plays a vital role in shaping tidal patterns and will be the focus of our next discussion. Let your mind drift as we transition to the next phase of our journey, where we will uncover the solar tidal forces that complement the Moon's influence. The Sun's gravitational pull, though weaker than that of the Moon, is essential for understanding the complete picture of tidal dynamics. We will explore how the Sun's position relative to the Earth and Moon creates variations in tides, contributing to the natural rhythms that shape our coastal landscapes. Prepare to relax and immerse yourself in the soothing waves of knowledge as we continue to uncover the mysteries of tidal forces. With each passing moment, may you feel a sense of calm and tranquility allowing the gentle ebb and flow of the tides to guide your thoughts. The universe is a vast expanse of interconnected forces, and as we drift deeper into this exploration, let the soothing rhythm of the tides envelop you in a comforting embrace. As we continue our exploration of the physics of tidal forces, we turn our attention to the complex interactions that govern the rhythm of tides across our planet. In this section, we will delve into the fascinating world of tidal resonance phenomena, a crucial aspect that shapes how tides behave in different geographical locations. The concept of tidal resonance is rooted in the principles of wave mechanics, where certain conditions allow waves to amplify, leading to significantly higher tides in specific regions. This phenomenon is a beautiful illustration of the interconnectedness of celestial mechanics and local geography. Tidal resonance occurs when the natural frequency of oscillation of a body of water aligns with the frequency of tidal forces acting upon it. Just as a swing moves higher when pushed at the right intervals, bodies of water can experience amplified tidal movements when the gravitational pull of the moon and the sun coincides with the natural oscillation of that body of water. This synchronization can lead to what we call resonant tides. In essence, the ocean can be thought of as a giant basin, and the shape of that basin, along with the depth and surrounding landforms, can greatly affect how tides manifest in that area. To visualize this, consider a bathtub. If you gently push the water at intervals that match the natural oscillation of the water, you can create larger waves. In the ocean, this principle holds true as well. Certain locations, particularly estuaries and bays, can experience heightened tidal effects due to their unique shapes and sizes. The Bay of Fundy, located between New Brunswick and Nova Scotia in Canada, is one of the most famous examples of tidal resonance. Here, the natural frequency of the bay matches the frequency of the incoming tides, resulting in some of the highest tides in the world. The water level can rise and fall by as much as 16 meters, creating a dramatic and awe-inspiring spectacle. The geography of a location plays a crucial role in shaping tidal resonance. Narrow inlets, for instance, can funnel water and create more pronounced tidal effects. This is why you may notice that the tides are more extreme in certain areas compared to others. The complex interplay between the gravitational forces of the moon and sun, combined with the physical characteristics of the coastline, results in a diverse range of tidal behaviors. Each coastal region has its own unique tidal signature, influenced by the local topography and bathymetry. In addition to geographical features, the depth of the water also impacts tidal resonance. Shallow areas tend to experience more significant changes in water levels during tidal events. This is because the gravitational pull exerts a greater effect on the water in shallower regions. As the tide comes in, water is drawn towards the shore, creating a bulge that can lead to higher tidal heights. Conversely, in deeper waters, the effects of tidal forces are less pronounced, resulting in more subtle changes in water levels. Tidal resonance can also be influenced by the alignment of celestial bodies and their positions relative to the Earth. During the spring and neap tide cycles, the gravitational forces exerted by the moon and the sun can either combine or counteract each other, affecting the overall tidal range. During spring tides, when the sun, moon, and Earth are aligned, tidal forces are at their strongest, leading to higher high tides and lower low tides. This alignment can enhance the effects of tidal resonance in areas already predisposed to larger tidal fluctuations. Understanding tidal resonance is not just an academic exercise. It has practical implications for coastal management and marine navigation. Areas with significant tidal ranges can pose challenges for shipping and fishing industries, as vessels must account for the rapid changes in water levels. The knowledge of tidal patterns and resonant behavior can help mariners navigate safely through these dynamic environments. Additionally, Coastal communities need to be aware of the potential for flooding during extreme tidal events, ensuring that appropriate measures are in place to protect infrastructure and residents. As we reflect on the beauty of tidal resonance, we also consider the concept of standing waves, which are a critical component of understanding how tides behave in resonant conditions. Standing waves occur when waves traveling in opposite directions interfere with one another, creating points of no movement known as nodes and points of maximum movement known as antinodes. In the context of tidal forces, standing waves can develop in bays and estuaries where the shape of the coastline allows for this interference pattern to form. The result is a dramatic amplification of tidal heights in these locations, showcasing the power of resonance. The interplay between tidal resonance and standing waves is a reminder of the complexities of our planet's systems. The ocean is not a uniform body of water. It is a dynamic and ever-changing environment shaped by a multitude of factors. The study of tidal phenomena, including resonance, is an ongoing endeavor that continues to reveal new insights into the behavior of our oceans. Scientists utilize advanced modeling techniques and observational data to better understand how tidal forces interact with the Earth's geography, climate, and other environmental factors. As we explore these ideas, it is important to appreciate the historical context of tidal observations. For centuries, humans have been captivated by the movements of the tides, using their knowledge of tidal patterns for navigation, agriculture, and fishing. Ancient mariners relied on their understanding of tides to make safe journeys across vast oceans. The ability to predict tidal behavior was a valuable skill, passed down through generations. Today, as we continue to study tidal forces, we honor the legacy of those who came before us, building upon their observations to deepen our understanding of these natural phenomena. In conclusion, the exploration of tidal resonance phenomena opens a window into the intricate relationship between celestial forces and terrestrial geography. The unique characteristics of coastal regions, combined with the gravitational influences of the moon and sun, create a tapestry of tidal behaviors that vary from one location to another. As we drift into a state of relaxation, let us carry with us the knowledge of how these forces shape our world, creating the ebb and flow of tides that have inspired awe and wonder throughout human history. Embrace the soothing rhythm of the tides, allowing their gentle movements to guide you into a peaceful slumber. The universe's gravitational dance continues, reminding us of the beauty and complexity that surrounds us, inviting us to dream of the ocean's depths and the mysteries they hold. As we delve deeper into the fascinating world of tidal forces, we arrive at an exploration of resonance and tidal patterns. The concept of tidal resonance is an intriguing aspect of how our oceans respond to the gravitational influences of celestial bodies. Tidal resonance occurs when the natural frequency of a body of water aligns with the frequency of the tidal forces acting upon it. This alignment can amplify the effects of the tides, leading to significantly higher tidal ranges in certain locations. Understanding this phenomenon requires us to consider the unique characteristics of different bodies of water. Each oceanic and coastal region possesses its own natural frequency, influenced by factors such as depth, shape, and the surrounding geography. When the timing of the tidal forces coincides with this natural frequency, resonance enhances the tidal amplitudes. This can create striking tidal patterns that vary dramatically from one location to another. For instance, the Bay of Fundy in Canada is renowned for its astounding tidal range, which can exceed 50 feet during peak tides. This remarkable variation is largely due to the unique shape of the bay, which acts like a funnel, amplifying the incoming tidal wave. As the tidal wave enters the bay, it travels at a speed that matches the natural oscillation of the water in the bay, resulting in a resonant effect that significantly raises water levels. In contrast, some coastal areas experience minimal tidal variation, These regions often have geographical features that do not favor resonance, leading to more subdued tidal changes. The interplay of geography and tidal resonance is crucial in understanding the diverse tidal behaviors we observe around the world. The concept of standing waves is also integral to the understanding of tidal resonance. Standing waves occur when waves traveling in opposite directions interfere with each other, resulting in a wave that appears to be stationary. In the context of tides, standing waves can form in bays and estuaries, leading to pronounced tidal bulges. These bulges can shift and change shape with the movement of water, creating dynamic tidal patterns that can be both mesmerizing and impactful. The effects of resonance on tidal heights can be profound. In some cases, resonant tides can lead to flooding in coastal areas, particularly during extreme weather events or when combined with storm surges. This highlights the importance of understanding tidal resonance not only for scientific curiosity, but also for practical applications in coastal management and disaster preparedness. As we explore the various examples of resonant tides, we find that certain locations around the globe are particularly notable for their tidal phenomena. The Severn Estuary in the United Kingdom is another prime example, where the tidal range can reach over 30 feet. The estuary's unique geography contributes to its resonant behavior, illustrating the powerful connection between physical features and tidal dynamics. In addition to the Bay of Fundy and the Severn Estuary, there are other regions where tidal resonance plays a significant role. The Gulf of Mexico experiences a more subdued tidal range compared to the aforementioned locations, yet it still exhibits interesting tidal behavior influenced by the surrounding landmasses and ocean currents. Each location tells a story of how tidal forces interact with the Earth's features, shaping not only the landscape, but also the ecosystems that depend on these tidal rhythms. As we consider the broader implications of tidal resonance, it becomes clear that these phenomena are more than just scientific curiosities. They are essential components of the Earth's natural systems, influencing marine life, coastal ecosystems, and even human activities. The tides play a crucial role in nutrient cycling, as the movement of water brings oxygen and nutrients to marine organisms, supporting biodiversity in coastal habitats. The relationship between tides and marine life is intricate and interdependent. Many species have adapted their reproductive cycles to align with tidal patterns, taking advantage of the ebb and flow of the tides to facilitate spawning or feeding. For instance, certain fish species may time their spawning events to coincide with high tides, ensuring that their eggs are carried into more favorable habitats. This synchronization with tidal rhythms highlights the importance of understanding tidal forces not only from a scientific perspective, but also from an ecological one. In addition to their biological significance, tidal forces have cultural and historical importance as well. Coastal communities have relied on the rhythms of the tides for generations, shaping their fishing practices, navigation, and even their folklore. The ebb and flow of the tides have inspired countless stories, myths, and traditions that celebrate the connection between people and the sea. As we transition to the next aspect of our exploration, we will delve into how tidal forces interact with Earth's rotation. The interplay between these two forces creates a complex relationship that influences not only the tides, but also the Earth's overall dynamics. Understanding this interaction is essential for grasping the full extent of tidal forces and their implications for our planet. Earth's rotation plays a crucial role in shaping tidal patterns. As the Earth spins on its axis, the gravitational pull of the Moon and the Sun creates bulges in the oceans, leading to high and low tides. However, the rotation of the Earth also introduces additional complexities to the tidal system. The Coriolis effect, resulting from the Earth's rotation, causes moving water to deflect to the right in the northern hemisphere, and to the left in the southern hemisphere. This deflection influences the direction of tidal currents and can lead to variations in tidal patterns across different regions. The concept of tidal locking is another fascinating aspect of this relationship. Tidal locking occurs when an object's rotation period matches its orbital period around another body, resulting in the same side always facing the larger body. The Earth and the Moon are in a state of tidal locking, meaning that the same side of the Earth always faces the Moon. This phenomenon has significant implications for the Earth-Moon system, including the gradual slowing of Earth's rotation over long periods. Tidal friction is an important consequence of this interaction. As the tides move across the Earth's surface, they create friction against the ocean floor and coastal features. This friction dissipates energy and leads to a gradual transfer of angular momentum from the Earth's rotation to the Moon's orbit. Over millions of years, this process has resulted in the Moon gradually moving away from the Earth, currently at a rate of about 3.8 centimeters per year. The long-term effects of tidal forces on Earth's rotation are profound. The gradual slowing of the Earth's rotation has implications for our planet's climate, day length, and even the stability of its axial tilt. These changes, while occurring over vast timescales, underscore the interconnectedness of the Earth's systems and the importance of tidal forces in shaping our planet's history. As we reflect on the intricate relationship between tidal forces and Earth's rotation, we gain a deeper appreciation for the dynamic nature of our planet. The tides are not merely a result of gravitational pull, they are a manifestation of the complex interplay of forces that governs our world. This understanding invites us to consider the broader implications of our connection to the oceans and the celestial bodies that influence them. As we move forward in our exploration, we will examine the ecological impact of tidal forces on marine life and coastal ecosystems. The relationship between tides and biodiversity is a crucial aspect of understanding how these natural rhythms sustain life in our oceans. Tides significantly affect marine ecosystems, shaping the habitats where countless species thrive. The rise and fall of the tides create dynamic environments that support a diverse array of life. Intertidal zones, the areas between high and low tide, are particularly rich in biodiversity. Organisms in these zones have adapted to the changing conditions brought about by the tides, resulting in unique ecosystems that thrive in this fluctuating environment. The relationship between tides and biodiversity is evident in the reproductive cycles of many marine species. For example, certain species of crabs and sea turtles time their spawning or nesting activities to coincide with specific tidal patterns. This synchronization ensures that their offspring are released into the ocean during favorable conditions, maximizing their chances of survival. The tides provide a vital link between different stages of life, facilitating the movement of larvae and juvenile organisms to suitable habitats. Coastal habitats, such as estuaries and mangroves, also benefit from the influence of tidal forces. These ecosystems rely on the regular influx of nutrients and sediments brought in by the tides, creating a rich environment for a variety of species. The ebb and flow of the tides help maintain the health of these habitats, supporting both marine life and the communities that depend on them. The cultural importance of tides in fishing communities cannot be overstated. For generations, coastal populations have relied on the rhythms of the tides to inform their fishing practices. Understanding tidal patterns allows fishermen to optimize their catch, as certain species are more abundant during specific tidal conditions. This knowledge has been passed down through generations, forming an integral part of coastal culture and tradition. As we conclude this section of our exploration, we find ourselves at the intersection of science, ecology, and culture. The tides, shaped by the gravitational forces of the moon and sun, are a powerful reminder of the interconnectedness of our planet's systems. They influence not only the physical landscape, but also the life that thrives within it. highlighting the delicate balance that sustains our oceans and coastal environments. As we prepare to transition to the next topic, we will delve into human interaction with tidal forces, exploring how we harness tidal energy as a renewable resource. This exploration will further illuminate the relationship between our species and the natural rhythms of the Earth, revealing both the benefits and challenges of our engagement with the tides. Tidal energy, derived from the gravitational pull of the Moon and Sun, presents an opportunity for sustainable energy production. As we face the challenges of climate change and the need for renewable energy sources, the potential of tidal energy becomes increasingly relevant. This form of energy harnesses the predictable movements of tides to generate electricity, offering a clean and sustainable alternative to fossil fuels. Across the globe, various tidal energy projects have been developed, showcasing the potential of this renewable resource. From tidal turbines positioned in coastal waters to tidal barrages that utilize the difference in water levels between high and low tides, innovative technologies are being employed to capture the energy of the tides. These projects not only aim to provide clean energy, but also seek to minimize environmental impacts, ensuring that our pursuit of energy does not come at the expense of the ecosystems that rely on tidal rhythms. The mechanics of tidal turbines are fascinating. These devices operate similarly to wind turbines, converting the kinetic energy of moving water into electricity. As tides flow in and out, they drive the blades of the turbines, generating power that can be fed into the grid. The predictability of tidal patterns offers a significant advantage over other renewable sources, providing a reliable and consistent energy supply. However, the harnessing of tidal energy is not without its challenges. The construction of tidal energy infrastructure requires careful consideration of environmental impacts, particularly on marine ecosystems. Balancing the need for renewable energy with the preservation of delicate coastal habitats is crucial. Ongoing research and technological advancements aim to address these challenges, ensuring that tidal energy can be harnessed sustainably.